This is IB HLAA, Probability and Statistics, day number 10. Should be a 10. Today we're going to talk about probability density functions for continuous random variables. And when it comes to probability density functions, the fact that they're continuous and in many cases differentiable means we can use some calculus topics. So different graphs that you could see potentially for a PDF is, for example, here's two different functions. We could see, a continuous curve that's differentiable. And let's say, we've got boundaries of, let's say, A to B. And let's take a piecewise function. Let's say also from A to B. With kind of a special feature here. We'll call this B actually, and we'll go out here to C. Okay, so with a probability density function, what we end up working with is that the area under the curve about its domain should equal 1. That's true of all probability density functions. And these functions depend on the type of distribution. So, for example, one that we've alluded to in the past, in the last lesson, was the probability density function for the normal curve, right? Dependent on the two variables sigma and mu. This is the probability density generating function for a normal curve. So, for example, up here, let's say this was normal with mu and sigma. What you would end up seeing is, of course, this is continuous for all real numbers, so that would continue on forever. But we could utilize this to determine the function's output. So, for example, in this particular density function, the mean is actually also the mode, right? Because of its properties and how symmetric it is. Okay, and the mode isn't always equal to the mean. So if we look at this PDF over here, the mode would be, in this case, B, even though it might not be kind of the midpoint of the graph with regards to the probability, right? So let's say that half of the distribution accumulates up to this point. This point would be called the median, right? The median would be the value we would call m, such that the integral, or the area accumulated from a up to m of, let's call it f of x, is equal to a half. Right? So there's the median. The mode is the output, or the probability. In this case, mu is the mode because it is the probability that comes out to be the largest. We're going to talk a little bit about variance, about expected value, and a couple other items as we get into this. So let's take a look at some properties below. A probability density function's outputs are always positive, seeing that probability is always greater than or equal to 0, less than or equal to 1. The area under the curve from negative infinity to infinity should equal 1, unless otherwise restricted based on some values. And the probability that x lands between two particular x values is the integral from one to the other on that function. Okay, let's go ahead and get into some examples. Okay, so here's an example of a continuous random variable x that has a PDF given. Okay, you can see that this is piecewise, and k is some constant. Looks like greater than 0. Okay, so we can see that our domain is not all real numbers. You can see that we're kind of operating on this interval from 0 to 3, right? And then our probability is 0 otherwise, anywhere outside of that interval. So the first thing we've got to do is find that constant k, and we can use our first property. And that first property says that the integral from 0 to 3 of this function should equal 1. So I'm going to split that up and say that the integral from 0 to 2 of f of x, which in this case is k, plus the integral from 2 to 3, which in this case on that interval is k times 2x minus 3, should come out to equal 1. Now we've got this constant k, we should be able to operate and solve this. Okay, I integrate the first, finding the antiderivative. I'm going to evaluate from 0 to 2. I'm going to factor k out in the second and find the antiderivative, which would be x squared minus 3x. And again, evaluate now from 2 to 3 on that, expecting the outcome to be 1. Okay, let's continue with our algebra here. If I operate on this, evaluating, I would get 2k minus 0k, which is 2k. On the other, I would get k times 9 minus 9 minus 4 minus 6. Okay, so let's simplify. That's 2k plus k times 0 minus a negative 2, which will also be a 2. Thus, 4k is equal to 1. Therefore, k is equal to a fourth. Okay, so good start there. Let's continue and sketch a graph of the PDF. Okay, so I'm going to try to make sure I can see the piecewise function above. So I'm going to go from 0 out to 3. And I can clearly see that if k is a fourth, okay, so let's operate here. If k is a fourth, this first part of the piecewise up here will go from 0 to 2, non-inclusive at 2, and that would be that portion of the PDF. The second portion, it's kind of important that I can see that f of x on the second interval is going to be equal to a fourth of 2x minus 3. And you'll notice that that's going to be linear. So let's find the output at 2. That would be 1/4 times 4 minus 3, which is 1, which is a fourth. So it'll kind of fill this void here. And then f at 3 is going to be a fourth times 6 minus 3, which is 3, which would be 3/4. So we would have an output of 3/4 way up here. Okay, so I can see a linear function. There's my PDF. So the area under the curve above the x-axis beneath the red and blue graphs should equal 1 if we integrate from 0 to 3. Okay, so there's our PDF f of x. All right, let's take a look at the following probabilities, of which clearly I failed to write these out. Okay, so our first probability we're going to find is the probability that x is less than 2. Okay, so the probability that x is less than 2 is going to be the area from 0 to 2. Now, just because it's less than 2 doesn't mean that it's any different than if it were less than or equal to 2. Because the area at 2 is not actually have any width, we don't have to consider that. So this actually would be equal to the probability that x is less than or equal to 2, which I can then take and find the area under the red curve, which would be 2 minus 0 times a fourth, which of course comes out to be a half. So we can see then that the area from 2 to 3 would also have to be a half. Right? We could kind of make that generalization. Okay, second probability. Let's find the probability that x is between 1 and 2. Okay, so that's the area from 1 to 2 under that curve, which would be 2 minus 1 times a fourth. So that probability would be 1/4. Let's move on to one that maybe is a little bit more interesting. Let's find the probability using some, oh gosh, I lost it. Where is it? Oh yeah, conditional probability. Found it. It was in there. It was just hiding. Let's find the probability that x is greater than 1 given that x is less than 2.5. Okay, so let me split this graph up into some regions. And I'll just tell you I did this work on the side, but this first area is a fourth, the second area is a fourth, This third space is 3/16, and the fourth space has to then be 5/16. Okay, so let's look at the probability that x is greater than 1 given that x is less than 2.5. Well, how you do that is you find the probability that x is both, right, greater than 1 and less than 2.5 over the probability that x is less than 2.5. Okay, so let's shade this region in. Let's shade in the region here. Right, that'll clearly be this region here. Okay, so that value comes out to be 4/16 and 3/16 added together, which would be 7/16. Okay, highlighter, where are you? There you are. Okay, and then the probability that x is less than 2.5, I'm just going to kind of sketch around it. I'm going to do a little yellow box around it. Would be that area, which would be a half, which is 8/16 plus 3/16, which would be 11/16. Now, if I simplify that, I come out with 7/11. Okay, that's a decent example of a non-calculator example of PDF. Let's get on to a calculator PDF. Okay, so we are going to work with this concerning this situation in a calculator active mode. Okay, so if you don't have your calculator, go get it, pause the video, and come on back. Okay, so I failed to ask in this question for you to find the value for C. Right, so I'm gonna call capital A our first part to this question, then we'll move to lowercase a. So to find C, what I want to do is very similar to part A in the previous problem. Okay, I want to say that the integral from 0 to 4, clearly based on this PDF, that's our only restriction here. That's our domain. Okay, so 0 to 4 of f of x, and I'm actually going to type, let's go like this. I'm going to type this. Let me highlight it. This is going to be y1. Actually, I won't highlight it. I'll write it right here because I'm about to compile like a library of these things. So I'm going to type y1 in as x4 minus x squared. Okay, so I'm going to take the integral from 0 to 4 of y1 times c, and I'm just going to solve for c, setting this equal to 1. Okay, so I end up getting, for y, this integral, right, this integral right here, I end up getting like 21 1/3. Okay, so if that's equal to 21 1/3, then c is equal to 1 over that value. Now, I'm storing these values in my calculator. If you're not good with that, right, then get good with that because it's important. So when I take c, or excuse me, when I take 1 over that number, I end up getting this value 0.046875. So I stow that as c. So now I have in my calculator, here's a library, c is equal to 0.046875. Okay, so that's stored in my calculator. Now let's move on to lowercase a. Okay, so uppercase a was our process for finding that value c, and now we can operate on everything else. Okay, the mean of f of x. Let's look back to what the definition of the mean or the expected value was. All right, in any probability distribution, what we took was we took each of the x sub i's times the probability of those values, right? And we summed them all up. So I missed my sigma notation here, but I should go from I equals 1 to the nth possible outcome. Okay, we're going to do something very similar here. We're going to take the integral from 0 to 4 of what I'm going to actually define as y2. And y2 is going to be c times x times y1. right? So that's c times y1, which is f of x, right? And we are going to multiply that by x. So essentially what we're doing is y2 is x times f of x, right? Which kind of mimics the expected value. Okay, so I'm going to take the integral from 0 to 4 of y2, and that comes out to be a 1.6. Okay, so we're using our calculator. Comes out perfectly to be 1.6. That's great. Okay, let's look at the mode of f of x. Okay, now in order to work with the mode of f of x, what I want you to notice is that if I look up here at f of x, right, f of x is actually going to equal c times x cubed plus a bunch of stuff. And I don't really care about that bunch of stuff. All that tells me is that the end behavior is going to look kind of like this, right? A cubic with a positive leading coefficient. I know c is positive, therefore it should look like that. Also, I know a couple things. I know that f at 0, if I were to plug a 0 in there, I would get 0. And f at 4 is going to equal 0. So kind of generally looking at the PDF itself, if I were to have the origin here, clearly the origin would be a 0 of the PDF, and actually the other endpoint is a 0 of the PDF. Now, my assumption, and I don't know this for certain, but I know that there's some kind of turning point at 4 potentially, but let's see. Okay, so how we would do this, right? If you have an example like the previous one where your PDF looked like this and like this, right? It's pretty clear that you can't work with calculus to find the mode, right? So we would just have to sketch and see that the mode was at x equals 3. All right, so that would be the mode of our distribution. But here we can use some calculus. So I'm going to take f of x, and I'm actually going to expand the x times 4 minus x squared. Okay, and if I expand that, I actually get c times x cubed minus 8x squared plus 16x. And I'm going to use some calculus here, find the derivative. This will help me to determine, what's happening at these values, or how the function is behaving around them. Okay, so our derivative would be c times 3x squared minus 16x plus 16. Okay, I'm going to set this equal to 0, finding the critical values of our PDF. And I'm going to factor. So if I factor, I get 3x minus 4 times x minus 4. That tells me that f prime of x equals 0 at x equals 4/3 and x equals 4. Now, I could go on to work with the second derivative test, but I know this, right? I know that there's no reason for 4 to be a max value. If 4 was a max value, then our PDF would have to look like this. But I know that end behavior, that's not going to work. So what our PDF is going to look like is, of course, I'm not including this. This is dashed because, well, clearly for a reason. We don't include any values outside of 0 to 4. Okay, so our PDF should look something like this. So clearly x equals 4 can't be the mode, right? Because, well, first of all, the mode has to be positive because there has to be positive values for there to be an area accumulated to equal 1. Thus, our mode would have to be at x equals 4/3. Now, you could go about this a different way, but in this case, I just used end behavior to determine the mode. Okay, now, one little thing that I do want to note, that the mode represents a value, right, in this case 4/3, which is greater than or equal to the probabilities for all other values, let's call them A, that are not equal for A not equal to 4/3. Okay, now a distribution could be bimodal. What bimodal would be is that there's just two modes. All right, so if two values have the same output and those outputs are maximum or maximized, or maximums, local maximums, then we could have two modes. So be careful for that. All right, we got one more slide here and we'll be done for this chapter's lessons. Okay, the median. We talked briefly about the median. Let's say I have a PDF, right, like I do here, and it looks kind of like this. Right, we got this situation going on where this is x equals 4 and 4/3. Well, the median is some value m. Now I'm putting this in a arbitrary location, but some value m such that, right, such that the integral, in this case from 0 to m, of our function f of x is equal to 1/2. Okay, so in this case, what we want to do is we're going to take and integrate from 0 to m of f of x, and I think that was y2, I believe. Maybe it wasn't. Can't recall. Anyways, it doesn't matter. We're going to do this part without a calculator because it really doesn't help to use the calculator until the end. You'll see it in just a moment. Okay, so I'm going to take f of x, and f of x was c times x cubed minus 8x squared plus 16x. We're going to set that equal to 1/2. Okay, so that would be equal to c times x to the 4th over 4 minus, let's try that again, 8x cubed over 3 plus 8x squared. And that is evaluated from 0 to m. Now, if I insert a 0, I'm going to get zeros across the board. So this is going to equal c m to the 4th over 4 minus 8 m to the 3rd over 3 plus 8 m squared. And of course, we want that to be equal to 1/2. Okay. So what I'm going to do is I'm going to make this look as simple as possible for insertion into the calculator. Okay, so what I'm going to do is I'm going to divide both sides by c and multiply both sides by 12. Right, that'll clear fractions. That'll get rid of c. So I'm going to divide both sides by c and multiply both sides by 12. So that'll give me 3m to the 4th, okay, minus 32m cubed. Okay. If I multiply this term by 12, I get 4 times 8, which is 32. Okay, continuing on, I would get plus 96m squared. And on the right side, I would get, if I multiply both sides by 12, I get 6 over c. Now, 6 over c, I'm actually going to insert into my calculator as y3. And 6 over c actually comes out to be a nice number of 128. So I'm going to plug that in. Y equals y3. And I'm going to plug this in as y4. Okay, so my objective then is to find out where those two intersect. So where those two functions intersect is where the median lands. And on your calculator, what you'll end up getting is that m equals 1.54. Now, a trick here is you got to consider window, right? So when you sketch this, or when you put it on your calculator, since c is 128, I would go up to at least 128, probably 150, right, on my window. So my y min, I mean, you can go 0 if you want. My y max, I'd go up to a 150. My x min, since I don't know where this is going to happen, I would go 0, and my x max, I would go out to 4, right? Our distribution goes from 0 to 4. Okay, so I don't recall exactly what this ended up looking like, but there's 128. If we went out to 4, I think the graph ended up looking something like this, right? And then this point right here ends up being x equals 1.54. All right, so we've got our median. Okay, hang on to this idea right here. This is your setup for median. All right, our last but not least is to find the variance. Now, we talked about this in lesson 1. The variance of any distribution is equal to the expected value of x squared minus the expected value of x quantity squared. Now, I already know the expected value of x. That was, I believe, 1.6. So I'm going to kind of hang on to that, okay? But the expected value of x squared is actually going to be the integral from 0 to 4 of x squared times f of x dx. Okay, so that's a new function we're going to type into our calculator. And actually, I believe, what did I do? I don't know that I defined that. I think I just took f of x and created a new function. I think I called it y5, and I called it x squared f of x. And I don't know if f of x was y2 or whatever it was, but I just took x squared times y2 or whatever I had defined f of x as. Okay, so if I operate on that, right, and I say the variance of x is the integral from 0 to 4 of y5 minus 1.6 quantity squared, I came out with a variance of 0.64. Okay, guys, there's some calculus, operating over the idea of statistics on this thing called a probability density function. Hope it made sense. Let me know if you got questions. See you in the next video.